Engine Performance Expo rolling along and even maybe winding down. We're going to ratchet up the conversation. We've got all this brain power in the room. We're going to put it to use in the next 30 minutes. We got Billy, we got Ben, we got Lake, there's me to just kind of even things out a little bit. But guys, we're going to talk valvetrain, area of expertise. You guys have worked a lot in this area. We're going to break it up into 3 segments, and it's going to be kind of interesting because this is, you can really mess a lot of stuff up if your valvetrain isn't right.
Yes.
So we're going to do 3 topics. We got 30 minutes, so we're going to be our version of Pardon the Interruption. So hit start, Joe. You got 10 minutes for this first section.
First subject, pushrods.
Right.
Begin.
Yeah. So think about it. In the old days, everything was about being light. Itty bitty thing.
Yeah, that little guy right there. Mm-hmm. That's out of a brand new LS3. That's what was run in the past. It's what's run today with most factory engines. Mm-hmm. It's 65 wall tubing. It's 2 welded balls. It's as light as it could be. But the thing is that you start modeling push rods.
Pole vault.
Yeah, modeling push rods are kind of interesting because when you start modeling a push rod, you just think, okay, well, it pushes straight down on it. Mm-hmm. Well, that's great on that side, but this side of it is rocking. Mm-hmm. Well, that little bit of rock right here, as this goes up and down, puts a small torque mm-hmm. on the end of this push rod. And as soon as you put a tiny torque on this, mm-hmm. you have moved from primarily trying to be in compression to now you excited a bending moment. Mm-hmm. So these things bend. Now, unfortunately, a lot of engines, you can take an engine like this that's designed for this, we can upgrade to this. Now this, instead of 65 wall, this is 105 wall.
Right.
So this is a much thicker wall, same diameter push rod, mm-hmm. Little bit heavier, lot stiffer, but still not nearly as stiff as this 80 wall that weighs the exact same mm-hmm. in a 3/8. But this 80 wall push rod, you've got so much more diameter, so it puts you in a far less bending. Mm-hmm. You know, Joe Mondello is one of my heroes. Grew up, loved him, think the world of him. And Joe and I were having dinner one time or at a conference, and we started talking. He goes, Billy, I've used, these push rods all my life. I've never failed one. And I go, okay. Mm-hmm. That makes sense. He goes, why do you think I need a bigger one if I'm not failing these 11/30 seconds? I said, well, Joe, have you ever failed anything else? He's like, well, of course I failed other things.
Spring,
rocker arm, studs, pulled the top of a head off. Yeah, blown everything up. I'm like, if you have a valvetrain problem, if the push rod fails, mm-hmm. there's a 99.99% chance it wasn't the push rod's fault. Something bound up, created enough force to fail the push rod. Mm-hmm. Or the ball didn't get enough oil and it did something. But it didn't fail because the push rod wasn't strong enough. But if anything else fails, it can be because the push rod stored energy, it bent, and then released the energy.
We made a diving board out of the push rod, right?
Right.
Like, we bent it, and that was okay. It didn't fail, but at some point it came back with way more energy than we expected to have in the system. So something else goes haywire then.
And people go, oh, okay, well, I'm going to use that. I'm going to use loft. I'm going to bend this, and I'm going to throw this valve up here for extra lift. And people do that in HRA stock eliminator all the time. The problem is you can do that perfectly at 1 RPM. Mm-hmm. So at 7,500 RPM, I bend this thing and I flick it and it rocks and it throws this valve over. Mm-hmm. But what happens at 6,800 RPM?
You missed the landing ramp.
Right, you land right back on the nose. Yep. And you saw that we were doing an NHRA stock eliminator deal together.
So it goes doink,
right,
doink,
and he's like, goes, Billy, I've got a dent in the middle of my camshaft and I got a dent in the middle of my valve. And it's like, yeah, you didn't clear. It's like one of these tabletops where you see these MX racers, they take off.
Exactly.
And if you do it right, you land on the end and you look like you're a professional.
You're Rudy Carmichael.
Right. You don't get enough velocity, you go up and you land in the middle of it.
You look like me.
Right.
Or you go the other way and you go more RPM.
Ooh, now!
You miss the whole entire ramp like Evel Knievel.
Exactly.
Land out in the parking lot.
Right, and you wonder why the valve seat looks like it's just all messed up and the valve springs are broken and everything. It's the whole thing. If I store energy here, I don't know where it's going to be released.
So in an effort,
No, we know it's going to be
make
released.
things-
We just don't know when and how much.
Right, it's going to it is going to be released.
So-
It's going to be released when you go from positive acceleration to negative acceleration, so we know when.
Right.
Where it's going to go from there,
hard to predict.
you bought the ticket, you're on board, you don't know where you're going.
That's why Keith earlier he said when he was going to look at the manifold, put the crash helmet on. He wouldn't have gotten to be there.
It's one of those things like, so in the effort to try to make it lighter, we lost the stiffness, which was more important than how heavy it was, right?
Exactly. I don't even know how much people think that the valve spring doesn't have to control the weight of the push rod. That's not true. It has to control it, but it only has to control half of it. So with a 2-to-1 rocker, if I go up from this 3/8 to this 3/8 80 to this 7/16 125, yeah, I put another 20 grams here, but I've only put 10 grams worth on the valve.
Not to mention you're on the slow side of the rocker arm, right?
That's what I'm saying. That's
Yeah,
why it's
yeah.
only 10 grams,
Yeah.
because
2 to
this is
1.
only moving there. The other thing is, what are my two components in the valve train that bend the most? Well, this lifter, dude, this thing's stiff. It doesn't bend much. If you have a decent sized camshaft, this camshaft's pretty stiff. It doesn't bend as much. But the push rod and the rocker arm are the two parts where you store energy. So you've stopped storing energy in the push rod and stopped storing energy in the rocker arm. And so now you have more control motion. But the valve spring still has to control it. So one of the things we'll do is, like in a race setup, we'll put the biggest push rod we can into it. And then we'll tune with wall thickness. And if you go, whether it's through comp or you go through somebody like Smith Brothers, through Manton, anything like that, most of these places will give you whatever wall thickness they want. If they won't, find somebody who will.
Right.
But you can sit there and get your length that you need, the biggest diameter fit, and then play with wall thickness as you're tuning.
So you can take some of the weight out.
Because you can take the weight out, you can run less spring if you take the weight out, but you don't want to do it by just playing with it. This was one of the days you talked about the trying to get these big stiff push rods. This was an aluminum matrix composite that we tried to push the end zone and then run through here. NASCAR and everybody else in the world made this thing illegal. This thing, we tried all crazy things. There was the beryllium stuff, and you look through the NASCAR rule book. I'm sure it says no beryllium push. Still push rods have to be steel magnetic. Whenever you get too creative, but there's neat things that have been done.
We've talked a bunch, Billy, in the past about how, because you're on that slower side of the rocker arm, I would definitely take more weight or more mass on my push rod to get the stiffness before I would take more weight on the retainer side.
Absolutely.
The valve spring works so much harder on that side than it does on the push rod side that you don't pay the penalty for that bigger push rod.
This weight isn't going to bend this push rod. In fact, it's going to bend this push rod less. This weight is not going to bend that rocker arm. In fact, it'll bend it less. But that weight will bend this rocker arm and will bend this push rod, so you're pulling back the bowstring more before you let go.
And that's what we're trying to avoid, is creating this, diving board, pole vaulting.
The uncontrolled release of energy. There's this energy flow up as the valve is accelerating, you're putting energy in the system, and then it's like a relay race. When you cross over max velocity, then the valve spring's taking that energy it's absorbed, putting it back into the system, and then in the closing ramp, we're back and giving it back to this push rod to grab this energy. So it's energy's flowing from this push rod into the spring, then from the spring back to this push rod.
The bow analogy is great.
You're
drawing it back as you're going over max lift, and then you're letting it go.
What you really want to do is draw it back and then let it control go back. You don't want to pull back.
Never release.
They say never release a dry bow.
Yeah.
Same thing with this. You don't want to release this guy without having it in control.
There you go. How are we doing time-wise, Joe?
We still have a minute and a half on this subject.
Oh, man, we're actually doing pretty good. So let's a little quick detour since we picked up the retainer. One of the temptations, because of the fact that this weight on this side is so important, a lot of guys will want to go with titanium retainers versus steel. So talk about the trade-offs on that.
There's a lot of pluses and minuses with titanium. Titanium is the same. When people tell you titanium's half the weight of steel and the same strength, that's only true if you're talking about cheap steels. if you go to your maraging steels, the strength to weight ratio is about the same between good titanium, 6Al4V, and a maraging steel or like an Aeromet 310 or one of the really good high nickel super alloys. They're not that much better. Titanium has a neat attribute in that it's a little bit, it has lower stiffness, so it doesn't want to vibrate. It kind of has a shock absorber technology to it. The problem is one of the things that we've learned with valve springs, I know that's kind of another subject, but valve springs are very, very sensitive to the distance to bind their run.
That's the next topic, by the way.
Yeah.
So in 15 seconds.
In 15 seconds.
Right.
So when we talk about
wow.
when we talk about this, which is one of these high nickel super alloy, type steels. When I put this and set this valve spring up, and I set it 50 thousandths from bind, it's always 50 thousandths from bind. The only reason it's going to get to be 60 thousandths to bind is if I have 10 thousandths seat erosion, where maybe I'll stretch a stem and maybe it'll change a little bit. But if I take this same weight retainer and make it out of titanium, it'll be twice the thickness. It'll be very close on the strength. From the valve spring, it won't know the difference, except what we'll know is titanium will wear over time. Because this valve spring is about 60 Rockwell. This titanium is about 45 Rockwell.
Right.
Over time, as this spring goes into its natural frequency, it'll be spinning in there, and it'll act just like a cutter, and it'll cut the retainer. And you'll get some of this install height where it's a time-based install height. Well, okay, I started out on 50 for bind, now I'm 55 from bind, now I'm 60 to bind. That's why all the NASCAR guys and all the pro stock guys basically went from the titanium to the steel. But I've done some stuff lately where we've done some tie valve springs for drag racing on these conical springs, and because of the dampening, these conical springs, they nest on one another.
Right.
When you run them real close to bind, that kind of dead blow hammer effect of that titanium retainer has been pretty nice. So I've been like telling people, no titanium, no titanium, no titanium. And then you're like, well, what should you do? Well, run titanium here. And they're looking at you and going, I thought you said never to cross the beams.
Yeah. Well, that's the thing about the tie retainer wear, right?
I got it.
Okay.
When you have that tie retainer wear, it goes all through your engine.
Oh, your motor.
And it wears everything else out, by the way.
Well, in driven oil, you knew exactly when somebody had a tie retainer.
Oh, yeah. With the oil analysis, you could tell. Boom, tie retainer, because your bearings are telling me it's unhappy about your tie retainer.
We talk a lot about, how does the guy know when it's time to change retainers when it's tie, and so that's one of the measurements that we have.
Yeah, we measure the thickness before, just like we measure margin.
That's right.
You're like, okay, it's down by 20%, 10%.
Yep.
Yeah, it needs to.
Yeah, absolutely.
In that distance to coil bind, the next topic, which we're late on by a minute
Well,
or two.
I felt like we were transitioning.
We are. We're blending. We're blending over, right? We're not crossing the beams, but we're blending over. Why is that important? Why is distance to coil bind something that really is important?
Well, you had me bring some show and tell. So I brought a little conical spring, and it has a strain gauge that we actually glued to the spring right here. So we have the coil that goes over here. Now, why we do that is, like on a conical spring, every coil is doing something a little differently. You can see the cross section here in the spring. Each one has a different diameter, a different spacing between them.
Right.
When those coils come together, a coil spring is really nothing but a wrapped up torsional spring.
Right.
So as you compress it, these things are bending and set up. But each of these coils has its own resonant frequency. It goes over here. I remember my wife did Montessori teaching. I remember going to her classroom, and you go in there, and she had like first, second, and third grade. And you see these boys; they're like 7, 8, 9 years old, and they're wiggling around and everything. And she would go, and she would kind of set her hand gently on their shoulder, and you'd see this kid kind of calm down. If you run a high-speed video of a spring, you can never make these coils stop jiggling on the base circle.
Right. If you've never watched one of the high-speed videos, just go to YouTube later. Right. Don't do it now. But go later and go Google or do a YouTube search for like high-speed valve spring video.
There's a ton.
And it will scare you to death like everything else we've shown
I mean,
you today already?
There's people who've left conferences I've given when I've done spring videos. I mean, they just got physically ill and they ran out. But the spring is moving like a bowl of Jell-O. These coils are surging up and down. What distance to coil bind does is it gives you one time each 2 crank rotations, each 1 cam rotation. It gives it one time to reset.
Just calm it down.
Just like my wife laying her hand on that kid's shoulder, this is your chance to lay your hand on the top of the spring and say, calm down.
It's gonna be
And
okay.
gives a time 0 for it. If you don't get close enough to coil bind, say you run something that's 200, people go, okay, I want this 900 lift spring. And I hear this all the time. And somebody goes, I've got this 900 lift spring, or I've got this 700 lift spring, or 650. Well, they think they get the 675 lift spring, and then they run a 500 lift cam, and because that's going to be easier on it.
Right. I got plenty of room. There's no way I'm going to get coil bind.
But now you're a 1/4 inch from coil bind at max lift, and these spring coils never stop oscillating.
Right.
Whenever we do a durability test, you can ask me about any durability test. Like this rocker is like 70 million cycles. Most of our deals are 1 million or 3 million. We're talking about the times the camshaft went all the way around.
Right.
For a valve spring, a cycle just means that this coil got close to that coil and back away. So you can
that's
have
happening more than the number of times the engine's going
exactly, and as that spring gets more and more active, your tack may have said you went around 1 time, but this coil next to this coil went back and forth 4 times. So as it came up, it went whoop, up, 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 and then came down, boop, 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 and then it's doing 3 or more on the thing. So it might say you said that was 1. It's like you do another riffle. It's like, what was that? Legolas and Gimli out there. They're trying to kill the orcs and everything. She pushes the ladder over, and Gimli's, that counts as 1.
Right. Yeah.
No, the valve spring doesn't count just 1 valve event as a cycle. It counts each time these coils get together and back. Yeah. That's 1.
Yes.
I like to think about it like if you had a mallet and you just walked up and smacked that spring, it would sit there and bounce. Well, the same thing happens when you come around off of the cam nose where I'm compressing that spring. I come back down and the cam's like, okay, you can rest now. And the spring's like,
I'm still going.
So it's counting cycles even though we weren't asking it to.
So what we use, to answer your question, what we use distance to coil bind is we use it for the best place we can dampen the spring and the best place we can reset any surge that happened from the opening or the closing.
It ends up being a great tuning tool. You
Absolutely.
can try different distances to coil bind on the system and go, it really liked 70 from bind more than 130, or 50 was better than 90, but it's something you can play with and tune.
Right, and if you really want to understand bind, you need to get a flow bench spring and check your lift with a flow bench spring, your real lift.
Well, see, that's the next topic, so you're jumping ahead again.
Okay, after you check your real lift, then you go and go to a spring checker and you check your real coil bind. Because too many people go in there and they go, okay, this is what the box says this bind's at. This is what my cam card says my lift is. They don't know their real lift. They don't know their real coil bind.
Right.
And then they think they've got, I've got 60 to bind. And you're like, you actually check it and they're like 120. And you're going,
right.
You don't have 60.
Another thing
So,
to be aware of.
by the way, you knew this is the reason why I laid these out in this direction, because I worked with a man long enough. I know the way his brain thinks. He's just going faster than our 10-minute clock. But let's go ahead and move on.
And it was a Lord of the Rings reference. Just
Talking about the bind, though, another thing to think about is if you've got multiple springs, you almost need to check what they bind individually.
Exactly.
Too, right?
Exactly.
Just my whole setup in my spring checker gets to bind at X, but I don't know if that was happening because of the inner spring or the outer spring. So I might be 50 from bind calculated, but my inner spring might only be 20, or it might be 120. So you really kind of want to check all of them.
And make sure when you're checking loads and when you're checking bind on the inner, you have to take into account the step of your retainer.
Absolutely.
Most retainers have 100,000 step. But, what's the motto of the British Royal Society, Latin Royal Society, where Newton worked and everything, was nullius in verba. It means take nothing from words, but it really means take nothing from granted.
Right.
Just because you think it's 100,000, get your calipers out and check in what it really is.
And the reason
don't
that step
assume.
is there is most of the time that inner spring is shorter than the outer spring.
Right. It should set up where usually when we design a spring, we design the outer spring to bind about 20 or 30 before the inner spring.
Okay.
It has generally a slightly lower frequency because it's got heavier wire, and it's easier to see bind. So generally we want this outer spring to bind first.
One other thing, Billy, is because we need that step, that inner spring shorter than the outer spring. So if I'm going to test this on my spring tester and I don't use the retainer with the step, I'm going to get a different load.
Oh, absolutely. That's where you need to have
you gotta have that step in there compressing that inner spring.
Yeah, you can kind of use a nickel for it if you want to, or get a 100,000th washer. I'm not going to say that it's ever been done that way.
Right.
You don't have to have the retainer, but you do have to have something that shims it, so you have to take into account the difference in height.
Yeah.
Final thought on that subject, moving on to our next topic.
Let's go ahead and move on to valvetrain stiffness, because that's the great point, is that this is going to have a big impact on the total that system distance to coil bind compared to your checking spring, because your checking spring is just not going to have any resistance, essentially.
So I think a couple of years ago, you've been doing this for a long time, this measurement of the system stiffness. But I think it was Jeff Smith that coined the phrase the GSR.
Yes.
So he calls this the Godbold stiffness rating.
Yes.
Right. Well, I mean, we kind of did this just about forever. You'd go in there, and the best way to know something is measure it directly, right? So if you want to know how stiff your valvetrain is, you just measure it. And it's like, well, man, that's hard to measure. It's like, well, no, it's not. You know what the lift is with the flow bench spring, and you know what the lift is with the real spring. You know what the load is of the real spring. It's pretty easy to go, what is stiffness? Well, it's how much something bends for a given load.
Right.
That is what stiffness is.
So for the same valve spring, you would see, if you had your checking spring on the flow bench and you had just easy math, I got 1 inch of lift, right?
Yeah.
You're probably going to see 1 inch of lift with both of these if you had a soft flow bench spring.
No, you could, even this one, there wouldn't be, you can put anything, the bending that you get with the flow bench spring, most flow bench springs aren't 10 pounds.
Right.
You're
No
looking
force.
at, most valvetrain systems are over 10,000 pounds per inch.
Yeah.
So putting 10 pounds on something that's 10,000 pounds per inch, it's
move
not going to move at 1,000th of an inch.
Correct, yeah.
So you're not going to measure the difference.
So to be clear for the audience that's listening, what you're talking about is the distance that we can bend or deflect our valve train in thousands of pounds per inch. So if you set a rating, like you just said, 10,000 pounds per inch, theoretically then if you were to apply 10,000 pounds of load to the system, it would move an inch.
An inch, right.
So luckily,
if
our
we do
system's stiffer
1,000,
than that.
it's 1/10 of an inch.
There you go, yeah.
If it's 100
thousandths,
it's 100th of an inch.
Yep.
Which is 10,000ths, right?
Yep. So at the end of the day, an easy test that everybody can make is you can just mock up your engine, right, and put your cam and your lifters and your push rods in, roll it around, and put a dial indicator out here on the valve retainer.
Yep.
See how much lift you get.
Yep.
Then take the really light load, checking spring out and put whatever springs you're really planning on using in there. Now you're going to have some real force. You take a
500
typical,
pounds, yeah.
Well, say the LS build for this is 675 open.
Yeah.
Yeah, there you go. So now I'm going to apply 675 pounds. Now, what you're going to do then is remeasure it and go, okay, that 675 pounds caused me to lose some of my lift. I'm not getting the same lift that I had before.
Right.
So then if you take the amount of lift that you lost,
It's it's going to be in pounds per inch, right?
Yep.
So it's the change in pounds divided by the change in inches.
Yep.
If you take something and you go 20 thousandths of an inch, over 675 pounds, you just take your 625, divide it by 20 thousandths, or 30 thousandths, 40 thousandths, whatever it is.
and so you're going to come up with a number. I always use easy math, and I go, okay, if I had 1,000 pounds of spring force and I lost 50 thousandths of an inch, 50 thousandths into 1,000, that's what, 20,000 pounds per inch. So if 1,000 pounds of load would bend my system 50 thousandths of an inch, then 20,000 pounds would bend my system a full inch. So the stiffness rating at 20,000 pounds per inch is now a number I can compare to, because I could now say, well, what if I took this push rod out and exchanged it with this push rod and did the whole test over again? You go, wow, I got some of my lift back.
Right.
You know what I mean? And so then that means my total system stiffness went up. Maybe now it's 22 or 23,000 pounds per inch. So you've got some levels like what.
And it's a really good combination for checking. Like, one of the beauties of this factory LS rocker arm is extremely light. Its stiffness per weight is great, but it doesn't have huge stiffness. So what you would see, like if you go into a good shaft mounted system, you're going, when you check your stiffness ratio with this push rod to this push rod, you're going to see a much stiffer with this 7/16.
Right.
125 than you saw with this 3/880. But you put it on that rocker arm because this is now your Herbie on stiffness.
Right.
You're not going to see hardly any difference in these. So you
Because
immediately know.
Right, because that's the weak point now.
So you never go to if you're using that rocker arm, if I saw somebody with that rocker arm and a 1/2-inch push rod, I'd go, oh, you've watched too much YouTube. You don't think, because it's not an optimized system. It doesn't matter. Y'all probably read the law of constraints where it talks about your Herbie. Your stiffness Herbie isn't your rocker arm. And then you see people that have a really nice shaft rocker and a 7/16 push rod and all this, and they have a 900 base circle camshaft.
Right.
And you're like, okay, well, that stuff's not your Herbie. Your Herbie is your camshaft that's bending. So the nice thing about this system stiffness is it's measuring the stiffness of your rocker arm, your push rod, your stands. Because people don't go into how much the whole stand, how everything's tied together.
And that's the big thing, like for the Expo build, like we're going to get to in here in a little bit, which is the long block part of it. Because of the supply chain challenges this year and everything, hey, we were going to have to use the factory cast rocker. And we were like, man, we have a lot of spring pressure. There's any way. So at the last minute, we found a set of Harlan Sharp aluminum, bodied pieces that had somewhat of a shaft type system. Not like this, but it was better than this. So we're like, okay,
better than stock body.
Better than stock. Yeah, better than stock. So we're like, okay.
Well, the tip on the stock body isn't designed to run 675 open, and it's not designed to run 700 lift.
Right. And so the idea is like, hey, we need to have something. Now, even though it wouldn't fit out of the box, fortunately, Jimmy and those guys, and we'll see in the video, improvised and made some changes and moved around and drilled and tapped and made it fit so it could get the job done, because we just knew that what we were asking it to do was exceeding the limits of that.
So one thing I want to go back to, Joe, I've known Billy long enough that he tends to say little gems that come out without actually, and I want to go back to something you just said a minute ago, because, you said, well, when I see guys with this rocker arm and a big push rod, I know they watch too much YouTube. But I want to clarify a little bit of that, because you said, well, this rocker arm is extremely well designed.
It's an amazing piece.
It has great stiffness to mass ratio. The problem is it is very light, which means it doesn't have a lot of mass. So even though the ratio of stiffness to mass is really good, the overall total amount of stiffness is still relatively low compared to, say, some steel, Jessel, Mohawk, professional rocker arm. So it wasn't that, oh, well, if you use a big push rod with this, you're going to gain a lot, because even though this is a well-designed rocker, it was designed intently for a specific application.
Right.
When you take it outside of that application, it doesn't really work anymore. So, I mean, you said that, but I just wanted to make sure that people got the value of what you were saying there.
It wasn't designed for these.
Right.
No, that guy right there, that's an 800 lift spring. If you run that spring with less than 700 lift, you're doing something wrong. But you can't run that rocker with over 700 lift.
Right.
So you can't. This is an amazing piece. This is an amazing piece. They don't go together.
It's not a system.
Right. It's not a system. And it's kind of like, you look at each little system, it's sort of like a position playing football. This guy's a defensive back.
Right.
It's light and quick, but doesn't want to be hit with something.
He's not a nose tackle.
Some of these rocker arms look like they're nose tackles. They're really heavy and bulky, but they're not designed to move very fast. Mohawk's more like your linebacker. It's kind of heavy and kind of can take a hit.
Yeah, right. It's a little bit of both. But I thought that was a really interesting point. Great stiffness to mass ratio. It's awesome because it's light, but because of those two things, you don't have a ton of stiffness overall.
Right.
We got a quick question. I don't know if we're taking questions.
Sure,
I think we are. Tim out there says, how much lift loss is related to rocker arm deflection? The rockers I use, meaning him, always measure 0.5 to 0.7 or so over the nominal ratio. When checking with the valve springs I run, the ratio is nominal. Thank you.
No, that's the whole deal. Is because as a valvetrain engineer, you know rocker arms bend. You know people check them. So depending on the application, you design the rocker arm cheated up about 3/10 to half a point of ratio, even up to 7/10 in some applications, because you know they're going to be checked. If I know they're going to be run with a 943 style spring that's 650 pounds over the nose, that, and I'm going to put a 400 lift lobe lift, it better come out with that spring to that rocker ratio. So when you buy a comp 1.6 rocker, it's actually 163, 165. When you buy a Jessel 1.7, Danny, forgive me, it's not 1.7, it's 173, 175.
Yeah, and
it'll be
there's compensation built into it.
Right, and that's what you have to do, because nobody sends a set of rockers back when it checks 3 or 4 thousandths too much in lift. But you just wouldn't believe, if I didn't lie on the rocker arms, the warranty, the return rates would go through the roof tomorrow.
And so one thing to be clear on too, though, is that the rocker ratio that's stamped on the box or on the rocker arm isn't technically what the ratio is. That's just some arbitrary point in the sweep.
And it's changing through the whole thing, like
your
you're
entire
implying.
geometry. Yeah, that's right. So sometimes even the way you set the rocker arm up will affect what ratio you physically achieve.
Oh, absolutely. You see the NHRA stocker guys will have a whole pile of push rods back in there, and they'll be changing it and changing the stud height just a little bit to change the ratio.
Which is amazing and underappreciated about NHRA stock eliminator. How crazy they are
they're
about what they're doing. Over
They
the
are
top.
amazing.
Like, you don't realize they're first out at 8 in the morning, but there's a lot going on. And time.
Boom! How about that?
Woo!
I told you, look how fast 30 minutes is going to go by, right?
Yeah.
Exactly 30 minutes again, Ben. You guys have really, really nailed it. Guys, I learned a lot right there. So much going on. Hopefully you took a lot out of that as well. And remember, you're going to be able to go back and watch this over and over again. Share it with your friends. We're going to do this again tomorrow also, so get some people, send out the link, expo.com, and bring in some more people. But right now, we're moving on to the next deal.
Yeah, we're going long block assembly. We're going back to Jimmy Barton's shop, and we're going to get the engine ready to go to Ben's, where we finally get it ready to go on the dyno.
Where Lake messes it all up.
Exactly.
What a day, what a day, what a day. My brain is swollen. I've learned so much today. They told us, don't start cars. We are not going to listen.